All right, so this is the notes for the lesson on linear relations. You actually started working with linear relations back in grade 8 and then a decent part of grade 9. So hopefully some of these ideas sound familiar, although in both grade 8 and 9 you never went into these topics in much detail, most likely. At least you didn't have to. And so in this course it becomes a foundational aspect of it. So while I'm going to front load with a fair amount of definitions of terms here, ideally a lot of these sound familiar already. With that said, let's get to it. So first, what does it mean if a relation is linear? That means, well, there's a few ways of explaining it, but I think the simplest is to notice the word line is buried in the word linear. And so if you graph a relationship that's linear, it always forms a perfectly straight line. That's it. We think of a graph, you think of a two-dimensional graph, there's a horizontal and a vertical aspect. And that means there's two variables. There's a horizontal variable and a vertical. And we call one of them the dependent variable, one the independent variable. Now first I'll say the independent variable is always on the x-axis. But what does independent variable mean? I'll get to that. And the dependent variable, we always graph on the y-axis. So that's just by convention. Whatever's the independent variable, we always show on the x. Whatever's the dependent, we show on the y. What does that mean? Well, I'm going to start with dependent variable. If something is the dependent variable, think what the word dependent means. Dependent means it relies on something else. So the dependent variable is what, to figure it out, you need to know the independent variable. Whatever that variable is depends on the independent. So for example, let's say you're making a graph of the relation between the number of people attending a party and the cost of hosting that party. So you're comparing two variables, cost and number of people. All right? So those are our two variables. So which one is the dependent variable? Well, the cost of holding the party depends on how many people you have, not the other way around. So in that case, cost would be dependent, so it would be on the y-axis. And number of people would be independent, and it would be on the x-axis. And so it's almost like a cause and effect relationship. And so as it says right here, this variable changes depending on what is on the x-axis, or the independent variable. So like I said, my example with cost and number of people is the number of people would be independent variable, the cost would be the dependent variable. All right, as well, a relation can be described as one of two different ways, either continuous or discrete. And so if something is continuous, the values in the graph we say are, we can say they are connected. Or you have a solid line or curve of some sort. Whereas if they're discrete, your data values are, your data values are not connected. Or they are just a series of points. So one, when you visualize it, is a solid line or a curve. One of them, when you visualize it as a graph, is a series of points. So how do you determine what's what? Well, this depends on the context. Let me go back to that example of comparing the cost of holding a party or whatever to the number of people attending, cost and people. In this case, if you want to think about that relationship between cost and people, that would be discrete. And that's because the number of people is going to be only, in that case, only whole numbers make sense. 0 people attend, 1 person, 2 people, 3 people, 4 people. But you can't have in between those numbers, in between 2 and 3, you can't have 2.6 people attending a party. And so for that particular relationship, that's an example of discrete data. You would have the costs for 0, 1, 2, 3, 4, 5, 6, but not in between. Whereas other scenarios, it makes complete sense to have stuff in between. All right? So that's it, though. I know I front-loaded a lot of information here. Hopefully, at least some of it sounds familiar. Let's look at 6 relationships, and for each determine if the relationship is linear or not, and if the information is, if the data is, or just a relationship is continuous or discrete. So relationship 1, described in words. I want to think about the distance traveled when jogging at a constant speed. And so first let's visualize this as a graph. So we have distance, and what else are we comparing to? You're always comparing two variables. In this case, we're comparing distance and time, the time you're jogging. And now what's the independent variable? Well, the distance you run depends on how long you've been running. And the key here, it says you're running at a constant speed. So in this case, distance would be on the y-axis, time is on the x-axis. So again, because the distance you're running depends on how long you've been running for. That said, what would this graph look like? Well, if you're not running at all, if you haven't started, you have no distance. And then since you're running at a constant speed, it would be a straight line. So this is definitely a linear relationship. And again, it's a linear relationship because we're running at a constant speed. If it didn't say that, then we wouldn't know. Or if it told you you weren't running at a constant speed, then this graph would look more like this. Sometimes you speed up, sometimes you slow down. And that would not be linear. So for this, to know it was linear, really that word constant was key. All right, now is this discrete or continuous? This is continuous. And one way of explaining why I know it must be continuous is, well, let's pretend it was discrete. Okay, let's say this graph still was linear, but was actually a series of a whole bunch of points, not a solid line. So let's think about what that would mean. If that was the case, if this was discrete, then you would have a series of points, maybe really close to each other, but a series of points with gaps in between. And that would imply that when you're running, at times you exist, and then you vanish, and then you reappear later on, and then you vanish, and then you reappear later on, and then you vanish, and then you reappear later on. That makes absolutely no sense in this scenario. Whereas in the example I talked about a couple minutes ago about the number of people attending a party and the cost, in that scenario, discrete data made complete sense. All right, so in this example, this is definitely a linear relationship, and it's definitely continuous. Let's look at relationship 2. A person's mass, or their weight, versus the years from birth, so really their age, over the first 16 years of life. And I picked 16 because chances are a lot of you are about 16 years old, but also that's generally when people stop growing taller, around the age of 16. So let's make a little graph again. I don't need it, but it kind of can help things more visualize things. So I have two things I want to compare, two variables, weight or mass and age, which is like a measurement of time. So in this case, what's the dependent variable? Well, again, time is going to be on the x-axis. In this case, mass is going to be on the y-axis. Because as you grow up, your weight changes depending on your age. And so in this case, time is the independent variable, mass is dependent. And what will the graph look like? Well, it doesn't really matter too much. I just have to know if it's linear or not. Let's see, when you're born, you have some mass. You don't start at 0 when you're born. And then you don't grow like this. We're not, even trees don't grow like this. Trees slow down and speed up depending on the season. If we were to show how our weight changes over 16 years, there's, we have growth spurts and whatnot, but it's not linear. It's definitely not linear. So this relationship is non-linear. And is it continuous or discrete? For the same reason as before, this is continuous. Again, if it was discrete, that would mean this particular person exists and disappears in between those points of data. All right, relationship 3 and 4 are both tables of value. Now, both these tables don't have any context. I don't tell you what x and y stand for. I just say there's an x and there's a y. And when x is 0, y is 4. When x is 2, y is 12, and so on. So is this linear? We'll have a few choices. One thing, again, I could make a graph. And I'll start with that, but I'm not going to rely on it. So in this case, it's pretty obvious what's on the x-axis, the x, and y is on the y. And so if I was to plot this, I'd have to, without grid paper, I can only kind of make a rough idea. 0, 4 is, 0, 4 is there, 2, 12, 2 over 12 up, there, 3, 16 around there, and 5, 24 maybe up here. Okay. It looks like it's a line. It looks like these form a straight line, but I didn't use grid paper. I just, I can't really tell. So if I want to continue going down this path, I need to actually get some grid paper. And I want to actually plot these properly and then see if those 4 points really do follow a straight line, which is pretty easy, especially if you just grab a ruler. And there's nothing wrong with that. It's a bit time consuming, but there's nothing wrong with it. Instead, I want to see if I can figure it out just by looking at the table. And so it does look like it's linear, but I don't feel so great about that graph I made. And so instead, let me look at what's happening here. If something is linear, if you pay attention to how it changes as you go down, it should be always going up at the same rate, a constant rate. What do I mean by that? Well, let's look at this first step. From 0 to 2, the x goes up by 2, the y goes up by 8. Okay, that alone tells me nothing. Notice the next step, though. The x goes up by 1, okay, which is half as much as x went up before. And the y goes up by 4, which is half as much as it went up by 4. So even though they're different numbers, it's the same rate. And then again, as you go from 3 to 5, the x goes up by 2, and the y goes up by 8 again. So I can see that even though the x is not always going up by the same amount, it's going up by the same rate. In this case, every time x goes up by 1, y goes up by 4. And so I can see from that this is definitely linear. Now, is this discrete or continuous? Well, again, this is the relationship I gave you, a table. That table literally is 4 points, and so this is discrete. Remember, that's what I gave you. I gave you the table, and that table is just 4 points. In between those points, we don't really know what's there, so it's just 4 points. This is discrete. In fact, a table is pretty much always going to be an example of discrete data, although it may connect to something else. All right, so another relationship here, 4. Not a lot of differences from before. I can see already this is going to be discrete for the same reason as before. But is it linear or not? Again, I could make a graph. There's no x and y's this time, so if I were to make a graph, I'd call A on the x-axis, B on the y, although it doesn't really matter for just determining if it's a line or not. But again, let me try the same thing as before. Let me look at what's happening here. So in this case, when A goes up by 1, B goes up by 3. Okay. If it's linear, that should always happen, or that rate should be proportional to that. So next is A goes up by 1, B goes up by 3 again. So definitely this is linear, at least so far. And then A goes up by 1, B goes up by 6. So right there, I can see this is not linear. It's linear at first, but the whole thing is not linear. And for a relationship to be linear, it can't just be part of it. The whole thing needs to be linear. And so I will say this part right here. That part was linear, but then it broke down, so in the end it's not linear. And again, this table is just 4 points. If you graphed it, you get 4 dots. And if you were to graph it, your 4 dots would look something like this. 0, 0, 1, 3, 2, 6, and then 3, 12 would be much steeper. And so you would see it doesn't actually form a perfectly straight line, but again, I didn't even need that graph. The last 2 examples are looking at relationships described as equations. And again, this equation really just tells you a rule how to figure out y if you know x. Right? If I know x, I pick a number for x, times by 2, add 4, that tells me my y coordinate. Just like this table here told me what y is if I knew x, just for these particular numbers. In this case, I can pick any number. That's the main difference. So is this linear or not? Well, if I'm not sure, you could make a graph if you remember what these look like from grade 9, although again, it's not a big part depending on how much time you had on that. So I'm just going to make a table. And because the table seemed to help in my last couple examples. However, it's an equation that we're actually given, so I can pick any number I want for x. So I'm going to pick some nice, clean, simple, orderly numbers. I'm going to pick 0, 1, 2, 3, and then figure out what I get for y for each of these. So when x is 0, I take that 0 and I put it into the equation and see what I get out. 2 times 0 is 0. 0 plus 4 is 4. OK, that alone doesn't tell me anything. Try it for the next one. Put a 1 into there. 2 times 1 is 2. 2 plus 4 is 6. So far, I can now see when x goes up by 1, y goes up by 2. If this is linear, that should continue for all of these. And I'll see if that does work for when x is 2. Put in the equation. 2 times 2 is 4. 4 plus 4 is 8. And there's that same pattern. And if I put 3 in, I get 10. And I can see the same relationship occurring, where every time x goes up by 1, y goes up by 2, which means if I graph this, I know I'm going to get a series of points that form a perfectly straight line, so I know this is linear. Next, is this discrete or continuous? Well, this table is discrete, but that wasn't the relationship I gave you. This is what I gave you, the equation. And in that equation, x can be anything. Any number you think of you can replace x with, and if you plot all those points, you would get not just a series of points, but eventually a perfectly straight line, because there's any number for x. Any hole you can imagine in this line can be filled by picking the right, a certain number for x. So again, the table that we used, that is discrete, but the actual equation I gave you is continuous. And again, that may be a little more confusing for some than others, and it depends kind of how new this is to you. But again, that equation is continuous. Quite simply, x, you can put any number you want into there. There will never be a hole in this line. All right, last relationship, a different equation. X squared plus 4 equals y. Again, x can be any number you want, so I will say right off the bat, even though I'm going to make a table, this will be continuous. The same reason as before. But is it linear or not? Well, let's pick some numbers for x and y. And why not be boring and pick the same numbers? This time replace x with 0. Again, this equation tells me the rule for how to figure out y. So 0 squared is 0, 0 plus 4 is 4. Okay, so far that tells me nothing. I got to keep doing more. Replace x with 1. 1 squared is 1, 1 plus 4 is 5. So now I can see as x goes up by 1, y goes up by 1. So if this is linear, that should continue. Replace x with 2. You get 2 squared is 4, 4 plus 4 is 8, and right off the bat I can now see this is not linear. As x goes up by 1, y now goes up by 3. So this is not linear. And if I bother doing the next one, and you know I don't need to, but if I put 3 into there, I would get out 13. So in this case, the y got bigger by 5. So definitely nonlinear. I will say this relationship here, although it's nonlinear, it is something you'll look at a lot in grade 11, regardless if you take foundations or pre-calculus, especially pre-calculus though. This is what we call a quadratic relationship, not a linear relationship. It's extremely important. It's the foundation of pre-calculus 11, really. Just like linear relationships will be the foundation of this course. But we're not in that course, so I'm going to erase it. Okay, because the question for each was, is it linear or not? Is it continuous or discrete? All right, the last example is quite, it's quite helpful to have a calculator with it. So I got a calculator here. So what's the setup here? It says the following equation can be used to determine what a $10,000 investment is worth after t years. So that t we see there is in the equation right there. That's the exponent. When put into a savings account that earns 5% interest per year. So I have an equation here where A stands for the amount of money you have after t years. And so I want to sketch a graph of this over the first 60 years as this investment grows, and then I want to determine if this is linear or not. Honestly, most of my work will not be about determining if it's linear or not. Most of my work will be creating a decent graph. It shouldn't take too long, especially if I have a calculator. So of my two variables, A for the amount of money, T for the time in years since it's been investing, which one is the dependent variable? Well, it's the amount of money you have depends on how long the investment has been growing for. And so the amount of money is the dependent variable, and time is the independent variable. Notice in lots of examples, in fact most examples, time is on the x-axis. All right, and I tell you in the question, I want you to show how this grows over the first 60 years. And conveniently enough, each of these grid lines I'm showing can be multiples of 10. All good. Okay, but how do I label my y-axis? I want to start at 0, but how high do I want to go? Well, for that, I probably need to figure out, well, what is this investment going to be worth after 60 years? If I know what it's worth after 60 years, which is the farthest this goes along, then that probably tells me the biggest value I need. So how do I figure out what this investment is worth after 60 years? Very quick with a scientific calculator. Go back to my equation and replace t with 60. And really what I'm going to do is make a little table here. But instead of x and y, I have time and the amount of money. And like before, I have an equation. And so I'm going to go to my calculator, and I'm going to jump straight to 60 years. And so replace t with 60, I get 10,000 times 1.05 to the power of 60. And my calculator tells me a pretty big number, 186,791 and change. So I'm going to call this $186,792. So after 60 years, this investment is now worth almost $200,000. And so that's how I want to set up my graph. If I look at my y-axis, I want to go from 0 up to 200,000, which is quite pleasant actually, because that's 100,000 in the middle, and actually each of these grid lines ends up being 10,000, right? This would be 50,000 right here, and so on. And so now I have my scale set up, and why don't I plot that point? After 60 years, this investment's worth 186,000, so that would be about right here. Okay, I don't actually have a lot of work left now to finish off the question. Let's pick some other years. Let's pick after 0 years. I don't really need a calculator to know what's going to be after 0 years. At the beginning, I have $10,000. I know that. However, I could go to my calculator, and I could type in 10,000 times 1.05 to the power of 0, and my calculator will tell me 10,000. So I'll just put that in right here. And really now, if this is linear, any point I plot in between should form a point on this line like this. If it's not linear, it won't. So I don't really have to do much more to determine if it's linear or not. Let's pick 10 years, I mean. So go back to my equation and type in 10,000 times 1.05 to the power of 10. And after 10 years, this investment is worth about $289. So remembering that each grid line vertically is about $10,000, that's about right there. I can now see this is not linear. There's no way I can form a straight line that's going to connect to these 3 points. So I know right now, without a doubt, this is not linear. In fact, if I were to keep plotting more points, they don't have to plot every 10 years, but those are nice numbers. If I were to plot every 10 years, you would see something kind of like this. And so that's what the curve would look like. So it's definitely nonlinear. We actually call this an exponential relation. I've got to learn how to spell here, exponential, which we learn about in this course, but is a big part of pre-calculus 12 as well. However, it's not linear, so I'll erase that. Right? Lots of stuff we looked at. Again, connecting back how things change as a graph with equations, and that will become a foundation of all these next math courses. But that finishes these notes. The homework, again, I'm not going to write it down anymore. You have it already on that sheet. So I'm all done.